Hello again. We are back with the second part of the lecture 7. In this part, I'm going through the different measurement techniques in larger scale dimensional metrology, as well as different systems we are using. There are numerous systems to achieve the coordinates for the point or achieve our goal in larger scale dimensional metrology. In overall, we can categorize the measurement system in larger scale metrology in two different categories. The first one is the direct measurement, which is, if I want to give you an example, for example, total station, that you are using the distance and angle measurement to get the coordinates of the target. So basically we are measuring the distances and angles, so by using of direct measurement we get the coordinates of the point. But we also have indirect method. Again, if I want to give you an example for indirect method, is photogrammetry. So we don't directly measure any distance or angle. We just take an images, and then later on, using some mathematical model and transformation, we can transform the coordinates of the camera station to the points in the images. So this is the simplified version of the two measurement techniques that you can use in metrology. Let's start with the coordinate measuring machine, or CMMs. What is CMM? Is a mechanical machine, obviously, and that can provide you the 3D coordinates of the point on your small or large scale machinery. And I'm going through different types of that. But how it works is you have a probe that you can move the probe on 3 axes, and that can provide you the precise measurement that you can compare the coordinates of what you've measured on the object with the one which is in the design, so you can see whether the design is matching what you've already manufactured. So it's good way of checking that. It can be computer controls, or it can be manually controlled. We do have different type of the CMMs. The one you can see on the right hand side, this image here, you can see this is the fixed one, which can be used for the small scale object in metrology. We have a X, Y, and Z axis. You put the small scale object and it can measure the coordinates for you using this probe, so the probe can move and give you the coordinates. If you have a bigger machinery that you can't really put it in the fixed CMM, you might use the what we call it the free arm system, or gantry type in general, which are for larger objects rather than the small object. I put a video here to show you how it's actually working. So this is the example of the manually control. You can see the guy is controlling the machine, and it's the free arm. So I'm not quite sure whether you see that, but as the probe is moving in different parts of the surface in this example, it gives the coordinates on the screen, so that whoever is doing that, it can see the coordinates for different parts. So it's used to measuring the side of this surface and different points of that to get the coordinates. You can see the probe is touching the surface in different parts, and he can control it. Is another example that he's checking the measurement on the different parts of that machinery and the parts that is not easy to access. So you can see why we are using the probe, and you can see the coordinates here, X, Y, Z. So hopefully this gives you enough idea how CMM is working and how it looks like. I found it is easier to show in the video rather than talking about that, because sometimes it's easier once you see the video, you realize that, oh, okay, that's how it works. But when I'm talking 1 hour, you might not be able to visualize that. Okay, let's move on. That was the measuring the coordinates directly without means of the distance or angle measurement. You just had a probe that gives you the coordinates. But we also have different methods for distance measurement. You know one of them at least, or even 2 of them I know, because we had the laser interferometry in satellite geodesy a little bit. The concept is pretty much the same, but a little bit different in terms of the machine itself. But let's start with the very first one, EDM. So we all know about the EDM, so electronic distance measurement technique that we have in a total station, and the total station we are using nowadays is mostly based on the phase shift. You know, we have time of flight and phase shift techniques. We also have the reflectorless that you can directly read to the point without the reflector. So that techniques use the time of flight. So you know these techniques from automated surveying system, and I believe in COMS A, so I'm not going to repeat it. The next technique, which is pretty much you've heard, but it might be new in the principle, is laser interferometry, laser radar, and ultrasonic distance measurement. So many of them you might have heard of the name, but you don't know the principle and how they're working. I'm going through each of them individually and explain how it works. Laser interferometry is basically a precise method of determination of the relative distance, and especially for the short range is the perfect method, and it gives you the accuracy of 25 microns for the range less than 60 meters. So it's very good techniques for the short distance. How it's working is pretty much from what you've learned in satellite geodesy about the laser. Do you remember we had the INSAR technique, which worked based on the interferometry? It's pretty much the same, a little bit different. So we have a laser source here. From the image you can see we have a laser beam, and we have a beam splitter which split the laser in two different beams, and then it goes to the reference reflector, which is fixed and it's not moving. So if you want to know, basically the reference reflector and the reflector you put at the start, they basically at the same distance or same range, and then once you move that reflector in two different positions, so the returning signal, when they're coming back to the beam or beam splitter, they interfere to each other, so they create the interference pattern that you can see, point A, position A and B. And there is a fringe detector. We know about the fringe from satellite geodesy, so it's basically work based on the monochromatic wavelength detection, and then from the difference that you have between the phase of two returning signals, it creates different pattern which gives you the change in the path length. So it's basically relative distance, it's not absolute. So you're going to change your position from A to B, and it gives you the relative movement of that target. So to start off, you start from one position, and when you're moving, it gives you that relative distance to the first distance or D0 that you've had. So what are the advantages and disadvantages of this system? First of all, it's very precise over the short range. I told you it's like 25 micron, which is so good for the range of less than 60 meters. And it can track a moving target, pretty much like the tracking system we have in total station, that you can detect the target, and when you're moving, the total station is tracking that, so it can track the moving object, which is very good. It's reasonably mobile system, so it's not that heavy and bulky, so you can move it around. It's a portable system and can be integrated into other systems like angle encode or laser system to give you more precise measurement, but also it can be used for the flatness and tilt. I'm going to show you how. But the disadvantages for this system is, I told you, it does not provide absolute distance, guys. It only gives you relative distance. And also, it's like any other system, can be interfered or can be line of sight can be broken, especially if you're working, for example, in the environment that many people are moving around or the cars are moving around. This is not a good system at all, because once your line of sight is broken, you have to restart the system. Like do the reinitialization for the first distance. Do you remember I told you we always start from one point and then measure the relative distance? So you have to restart the whole system and start over. So this is not very good choice for the environment that they're busy, like the construction site or all those things. This is not a good system at all. And then you need to also make sure that you correct for any atmospheric error. I don't say this is disadvantage of this system. Many of the system can be interrupted by environment and atmospheric errors. So as far as you monitor and you make the correction, it's not gonna be an issue. Also, it's very expensive compared to what it can do. You can find a reasonably cheaper system to do the same job. Laser interferometry can also be used to check tilts, skewness, flatness, and alignment. What you can do, you use the dual reflector, so two reflectors within a distance from each other, and then you have two laser beams, so you have a beam splitter again, and then it goes to each of them because they are in two different distances. Do you remember when I explained the tilt, I told you we always measure if there is straight, which is not, sorry about that, if this is the line which is straight, and then you measure the distances. Yep. So these distances are equal if in this case this line is vertical, but if you have a tilt, this distance, if you have a tilt like that, this distance cannot be equal. So from that you can get a tilt. This is how it works. The next system I'm going to talk about is laser radar. It's pretty much like reflectorless total station, so the application is the principle is same. It's also similar to laser scanning, so it sends a laser beam but with much higher precision. That's why we are using laser radar, not laser scanning, because it has a more precise accuracy. And then you use the phase shift techniques to measure the obviously distances. So it has two frequency modulated laser beam, and it sends it to the object. There is no target required for this, so it's non-contact system. And then once they coming back using the phase shift methodology, it can measure the distance and which can give you the precise range of better than 30 micron, or you can also express it as a 20 micrometer plus 2.5 micrometer per meter. The good thing about laser radar is it can also use mirror or targets, mirror or prism, where you don't have access or you don't have direct line of sight. So if you, for example, want to measure something on back of the machinery rather than have the next station to measure that, you can use the same station but use a probe or a prism, or somehow measure the points that you don't have direct line of sight using the prism. So this is a good thing. We also have a bad or disadvantages of laser radar. It's pretty much like laser scanning. It can be affected by the material that you're using. Reflectness of the material is important, same as other techniques. Atmospheric condition also is affecting the laser radar, so you can't really use the laser radar in every environment. The last technique is ultrasonic distance measurement. Ultrasonic distance measurement is being used for a long time nowadays, but it's not really an accurate technique to be used, to be honest. So it's very limited area that you can use, especially for short range distances only. But because of its low cost, some of the people, they still prefer to use this distance rather than the more expensive one if they don't need to have very precise accuracy. And we know about the sonic distance measurement, which is for small distance. You might also have heard the ultrasound imaging, which is for medical science most of the time. Yeah, these are the applications. I just mentioned that because If you hear that system, you're aware of the existence, but this is not the preferred method to use. Here I'm going through some of the main larger scale dimensional metrology system, and we are going to explain each of them individually, but the list of them are laser tracker, laser radar, laser tracer, photogrammetric system, RGPS, and then we have medium scale system, and total station is the last one. The first one is laser tracker system. Laser tracker developed in mid-1980s, and is pretty much used for larger scale metrology applications. So if you have any big device, you might go for this laser tracker system. It falls into the category of centralized, contact, and active system. If I'm telling centralized, so it's one-to-one measurement system. Is contact, so you need to have a target, and it's an active system because it's using the laser. It emits the signal itself, and it's reflecting back and measure the coordinates or distance. So let's start how it's working. The fundamental principle is pretty much like any other laser system. The difference between the laser tracker and laser radar is laser tracker, it measures the absolute distance as well as relative distance, so we can measure both because it has interferometric laser interferometric system as well as absolute distance measurement, so that you can combine two system together and get the absolute and relative distance. It also have the angle encoder, so it measures the distance and angle. So it measures both vertical and horizontal angle. So it gives you the flexibility, and also it can follow the target. It's pretty much like a tracking system we have in the total station. It can also use the probe to get access to the points which are not in the line of sight. So if you have a big machinery that you are not able to access or put the target and measure directly, so you might use the probe. I will show you the example of that, and I put the video on the study desk that you can go and watch it. So you use them and measure to those points on the machinery that you don't have the access. We also have the software in the system that can measure the coordinates based on the angles and distance measurement. But just remember, it doesn't give you the coordinates directly. It's just the relative positions or relative coordinates, unless that you have the 3 known points to give you enough redundancy to be able to measure the coordinates directly. As I explained, laser tracker use angle encoder to determine the horizontal and vertical angle. As you can see, we have a servo motor exactly the same as the total station, and we have a beam splitter and interferometric system which can be used for measuring the relative distance. So I can measure both absolute and relative distance. As a target, we use the SMR or specific target, which is only for laser tracker. I will show you the example of that, and we are going through that. We also can measure the relative coordinates unless that you know 3 points either in the object space system or on the object for the redundancy to be able to get the absolute coordinates. Otherwise, it only gives you the relative coordinate change. The very first laser tracker, they used the laser interferometric system only to measure the relative distance. Then we started to having the absolute distance measure system, which combined to the laser interferometric system to be able to measure both absolute and relative distance. Where we used the absolute distance, it was like, as I said, for laser interferometric, we need to have the initial distance or D0. Good. So we have a datum to start off, and then we can get the relative change in respect to that datum. So how it works in laser tracker use that absolute distance measure to measure the datum distance, and then if you have any loss or line of sight blocked for any reason or interrupted, then you can reestablish the datum using the ADM. Good. And then you measure the relative changes using the laser interferometric system. So this improves the accuracy you can get from this system significantly, but there is still some deficiency in terms of it takes longer time to measure and the tracking system are slower. So these are the disadvantages of laser tracker system. This is the example of the specification I got for Faro laser tracker. You can see it can operate for the range 2 to 160 meter. It can operate both indoor and outdoor, and it's very portable. And the accuracy you can get for the distance is 16 micrometer plus 0.8 micrometer per meter. Obviously, you have to multiply this bit by the distance you're measuring to be able to get the total precision. I told you laser tracker, they're using their own very reflector, which is SMR or spherical mounted reflector, which can be used to precisely measure the point. The reason that we are using the spherical shape is it has a very precise centering, which within the accuracy of better than 3 micrometer. It also doesn't change the center, it's not changing as you rotate it, so this is another advantages. And it's very popular. It has the magnetic bracket, as you can see in the image. So what you can do, you just move this SMR to the next point, and usually they have a magnetic bracket in different parts of the object. All you do is just putting the target on the magnetic bracket or the pod or the bed, whatever you want to call it, and then they can measure it. So it's kind of walk around target, so it's very easy to move around. They use the SMR basically to establish of the datum or orientation in measurement space. They also use that if they want to monitor the object, say over the time they have an object, so they usually put these magnetic bracket in different parts of the object, and it stays there forever. So what they do, every time they put SMR, put it on these points, and then they can measure it. It's very useful tool for monitoring, and it gives you very precise accuracy. I'm going to show you the laser tracker video and how it's operating. I found the video is very useful, and it gives you an insight about the whole system. Let's watch it together.
Faro, the world's most trusted source for 3D measurement technology, develops revolutionary portable measurement and imaging solutions. Faro's commitment extends well beyond product performance and constant innovation in order to build an ongoing relationship with our customers and help make their products and processes the best in the world. The Faro Laser Tracker is an extremely accurate portable coordinate measuring machine that enables you to build products, optimize processes, and deliver solutions by measuring quickly, simply, and precisely. With the Faro Laser Tracker, you can produce more competitive products, accelerate product improvement initiatives, and deliver high-performing products for today's technical marketplace. The laser tracker measures 3D coordinates by tracking a spherically mounted retroreflector, an SMR, that is in contact with the object. Two angle encoders measure the elevation and rotational angles, while a highly accurate absolute distance measurement is used to determine the 3D position of the SMR. The software stores these values and allows for the comparison with CAD data. Dukin Group in France specializes in the design and manufacture of composite parts and subassemblies for various industries. They use the Faro Laser Tracker on their large molds and parts, such as antennas. They are very satisfied with the Faro Laser Tracker due to its high accuracy and large measurement range. The Faro laser tracker creates groundbreaking efficiencies in applications such as alignment, machine installation, component inspection, tool building and setup, and reverse engineering. Companies are saving millions of dollars by completing jobs faster, reducing downtime, eliminating costly scrap, and getting accurate, consistent, and reportable measurement data. At Faro, our focus is on simplifying our customers' work with tools like the laser tracker that empower them to dramatically.
So I put the video on the PowerPoint, so if you're interested to watch more, you can go, or you can search the internet to find more interesting laser tracker videos, but I found it useful that shows you how actually SMR is working and how the laser tracker is tracking the target, and you can measure the coordinates. The use of probe basically improves the flexibility of laser tracker system, so you can measure to the object that you don't have the line of sight to them. How probe is working is very simple. I can show you on the image. So the probe itself has 2 SMRs. Sometimes it comes with 3 SMRs. So the laser is measuring to this point A and B, and the distance between them, like distance 1, 2, 3, 4, is already known and measured. So what's happening? A laser is measuring to these 2 SMR, and based upon these parameters, it can give you the 3D coordinates of the probe tips. So you touch the tip to the points you want to measure the coordinates, and because all these distances are known and it's calibrated, so it can give you the precise coordination for that point. It's very useful for the point that you don't have line of sight, as I said, but also the accuracy depends on the geometry of the measurement, precision of the known distance on the probe. So if your probe is not calibrated and it's not really good, these distances are not really precisely measured, then the coordinates you get obviously is out, and it doesn't have that precise accuracy you want. Also, it depends on its alignment precision and precision of obviously laser tracker itself. So more SMR you have on the probe, it gives you better relative position or improve the final position for you. The probe itself can be static or dynamic. Static like what the example we have here, and dynamic by including other measurements. I put a video to show you how the probe is working. It's a simple or very short video. This is the Leica B probe. You can see this is the tip. This is the SMR, 3 SMR on the probe itself, and we are using that to measure the area which is in the, like you can't really measure this point by direct line of sight from laser tracker, so you use the probe as you can see, and then you measure the point which is on the back of the machinery where you don't have the access or direct line of sight. We also can use a robotic arm as a flexible and rapid probe to measure the points which are not in the direct line of sight or difficult to access. So this is the example. You can see it because the arm or robotic arm has different or can rotate in different axes, so you might need to get the rotation of the axis at each of these points to be able to get the coordinates of the point at a probe tip. So to summarize, I can tell you advantages and disadvantages of laser tracker. First of all, it's very mobile and portable. It can, you could see the range can vary from 2 meter to 160 range, and it can also measure the wide range of the volume and distances. There are options to using a fixed target like SMR or probes to access the points which are difficult to access or are not in direct line of sight. We also need to can have multiple stations. This system can be integrated to other systems easily to give you more option and more precision. Disadvantages is sometimes depends on the surface geometry and your machinery or whatever object you're measuring to can have less precision. You need to calibrate the point in a space or an object to have the precise coordinates, obviously, and then it's slower because it's one-to-one measurement, so you have to measure each point, so it takes longer time rather than like distributed system that you can measure everything at a time. So it's like one-to-one measurement. It's centralized system, so it takes longer. System must be moved to collect more object points because you can't really access all the points from one station. If multiple laser tracker is required, it's not cost effective, so you better use one distributed system rather than the laser tracker system. So to summarize, if I'm asking you in the exam, for example, what is laser tracker, you can use these bullet points and explain that, okay, laser tracker can measure the distance, either relative or absolute. It can measure the horizontal and vertical angles because it has the angle encoders. It can use the target like SMR or even probe. It also will measure the relative coordinates change unless that you have 3 known points, either in object space or on the object, which is calibrated and has a good precise coordinates, and then you can get the coordinates of the point. The next system I'm going to talk about is laser radar. Is centralized, again, is one-to-one measurement. And the next system I'm going to talk about is laser radar. Is one-to-one measurement, so it's centralized. It doesn't need a target, so it's non-contact and it's active. It's using the laser beam, obviously, to go to the object and coming back, and it can measure the distance and coordinates for the point. It's similar to laser scanner with much higher precision. It's basically can be used for matching the point class to the design specification and find out the accuracy requirement and dimension. So it can use cooperative target or prism. It's like a laser scanning. You need to have some kind of prism to match the point class together. Can operate in poor light conditions, so you don't need, it's not like total station. You can operate it at night, for example. It's relatively an expensive instrument. It can measure the range of 2 to 60 meters, which is lower the range of the laser tracker. If you remember, laser tracker could have measured from 2 to 160 meters. So the precision you can achieve is better than 50 microns. So the advantages of using laser radar is, especially for the complex surface, that you really can't put the target on that, or is very good for the inaccessible or unsafe environments. Say the surface is too hot, or there's a chemical system that you don't really want to send someone to put the target, or you even cannot use the probe. So if you want non-contact, precise instrument, laser radar is highly recommended. The third system is laser tracer. Is in the family of laser tracker. Is centralized contact, so you need to have a target, and it's active system. You can get the point coordination using the multilateration, so you are measuring the distances and then you can basically intersect them together, to get the points. So in 2D you need 2 distances, in 3D you need 3 distances. And there's no angle reading, so you can't really get the horizontal or vertical angle. It is very high precision system, and it's using interferometry system to track the target at very high precision. The precision is less than 1 micron. For tracking, it can be employed for a specialist task where the attributes of speed, size, and accuracy are critical factor. And to achieve the accuracy, but we have to remember geometry is very important, and you can't achieve the accuracy for any type of geometry. The next system is photogrammetry system. We had the whole module on precise close range photogrammetry, so you should know better now. First of all, it can be distributed and centralized. I'm telling you why it can be centralized. You might say, hey, you already told that photogrammetry is distributed system. Yes, I told, but it can also be centralized. I'm showing you in the next slide. Just be patient. And then it's non-contact, so you don't need to have a target, and it's passive. It's using the natural light source rather than sending a laser or sending a light itself. So photogrammetry is a very useful tool, especially it's very cost effective. It can give you a good accuracy of up to 100 microns over a small distance, and for many of application photogrammetry is preferred because it's low cost and it's movable or portable, and also you can achieve the accuracy with high precision. But you have to remember, to achieve that accuracy you have to have a good quality camera. You need to do the calibration. There is requirement for having the targets, and you need to be able to put them in a right position, and you need to have optimal geometry of camera stations and controls, and obviously adequate lighting if it's required, and all those things is changing the accuracy you can achieve for photogrammetry. I told you photogrammetry can be centralized or distributed. You probably know the distributed system, which is pretty much what we've discussed in the close-range photogrammetry, that you take an image or images from the whole objects. But we also have the centralized, which is this image on the right hand side. If we are talking about the small scale metrology, we might have 2 or more cameras in one system, and you sometimes have a probe even, that you can take an image very close to the object and get the coordinates, and it's going to be 1-to-1 measurement, so you basically get the coordinates for one point only. So it's 1-to-1 measurement then, rather than 1-to-many measurement, which is distributed. The next tool is our GPS or our space. It's not our GPS, don't be confused. It's just a name similarity, which I'm going to explain why they call it iGPS. Nowadays they call it iSpace as well. So first of all, it's distributed, so it's 1-to-many measurement. It's contact, so you need to have a probe, and it's active system. So how it's working is based on the traditional triangulation we had in surveying, so you must have known the principle by now. And how it's working is he's transmitting a laser beam in different planes, and then it has an intelligent probe. I'm telling you why it's intelligent, because it has the image processing software itself. And why we call it GPS, because the transmitter, which is this one here on the picture, is purely like our satellites. It's just emitting the signal, it's just dump. And then we have a receiver, which is, in our case, is this probe, which is intelligent and can calculate the coordinates based on the signal it's receiving and the information. This is the segmented view of iGPS or iSpace. Basically, transmitter includes the laser and infrared strobes, so it transmits both laser and infrared. Laser will be emitted like 2-fan shape, and is basically rotating through 360 plane. These fan shape basically are opposed at 90 degree, and each fan themselves are inclined by 30 degree to the vertical, and they are in opposite direction of each other. An infrared pulse also is emitted every second rotation. The precise timing and angle of the laser plane gives you the vertical angle, and the horizontal angle also can be determined using the infrared pulse, as you can see in the image. And then we also need minimum, so we can't really use one of them by itself. It's always required to have at least 2 transmitters to be able to get the 3D space coordinate for each point. So it basically comes from the fact that if you look at here, if you intersect two plane together, I told you it's going to be a line, not a point. So it doesn't give you a unique position. As you can see, this point can be higher up or lower, so it's not a unique point. To get the unique point using the two transmitters in our GPS, we still need to have extra information like about the coordinates of the station, also the known distance between them, which can be precisely measured by precise scale bar or invar or carbon bar. I've shown you the scale bar in the macro network when I explained that you're using the scale bar, so you need to have extra information to be able to get the unique position for that point, otherwise you can't with too many. Put a video to show you the example of the RGPS with the probe. So if I'm going further a little bit, because I don't have time, this is the example of the probe or tracking system. We have a network of RGPS transmitter. I told you it is always required to have at least two. Yeah, this one has a sensor because I'm showing you. This is the probe with the scanner, so you don't have to put it on one point, so you're scanning the surface. It's useful for getting the surface, and you can compare the point cloud you got from here with the design one. This is the example of the probe with 6 degree of freedom. You can see as he's moving and the line, you can see the line also is appear in the software. So hopefully it gives you an idea of how it works. Let's continue with RGPS. RGPS can give you the accuracy of 200 microns, which is acceptable, not as precise as laser tracker and laser radar, but the precision for RGPS also depends on the number of transmitter station, how many of them do you have, the physical measurement volume to define the maximum distance to the target. It's always critical to know what is the maximum distance you can have to your target, because it's really affecting the accuracy that you can achieve. And then it also depends on the geometry of the network with respect to the object itself, as well as the precision, coordinate precision of the transmitters itself. And I told you need to measure the distance also using the scale bar. How precisely you measure the distance between them is also affecting the final results. The next system I'm going to talk about is miscellaneous medium scale system. Basically a special system are including the laser projector. Is pretty much like a laser tracker. The system can give you an accurate coordinates of the point in 3D space. But rapidly moving mirror system in the instrument direct the laser beam, and it can you can have a shape on the surface of the object, like what you can see in the image here. This is especially useful where precision cutting or positioning of additional structure or bracket is required, and measurement marks are difficult to place on the object, so you can really put different measurement on the surface, and you want to have a shape on the surface which is very precise and very good. The last tool, which we all know, is the total station. You might say total station doesn't give you that precise measurement, but we do have a total station. We call it industrial total station that I'm going to explain, which gives you the more precise accuracy for both distance and angle measurement, which enable us to achieve the micrometer accuracy. But the problem with the total station, first of all, there are some advantages and disadvantages of using total station. First of all, it's very portable and lightweight. It also can integrate with other systems, which gives you more precision. Lens precision can change, obviously, whether you're using the prism or tracking or reflector lens. You might have different precision, but in general the angular precision is now is very good, somewhere between half a second of arc to 5 seconds of arc, so it's very precise. What we are using for metrology though is industrial total station, which is very precise in terms of the distance measurement, and it's also very precise in terms of the angle measurement, which the precision is plus or minus 0.3 millimeter plus 30 micrometer per meter. And this is for the reflect when you're using the target. If you're using direct reflex or reflectorless, then it's gonna come to 2 plus or minus 2 millimeter in volume space. Do you remember we had the volume accuracy, and I told you that this is one way of presenting the precision in metrology. And then the Leica TDRA 6000, which is the industrial total station. So this specification we are claiming is based upon this device. If you are using Trimble version or other version, you might have different accuracy. So anyway, it had typical position uncertainty of plus or minus 250 microns. You can see it's very much more accurate than the normal total station. So for a surveyor, medium scale for us is basically at the construction site. We do have too many medium scale, but for metrologists, any object which is 5 meter to 3 meter, we call it medium scale object in metrology. There are many large scale applications as well that we can use the total station. Examples is bucket dredger, large tunnel boring machine, tunnel surveys, bridge component construction. That for all of these applications you can use total station both for measurement and monitoring. The disadvantage of total station obviously is lower precision of total station compared to other measurement devices or systems that I discussed. But there are some advantages, which is mostly about the flexibility, portability, and it's also I can act as a laser tracker, so it can measure the absolute distance. Is non-contact measurement. You have the direct reflect or reflectorless option. You can also provide optical alignment in 3D space. It can use the, all know that total station nowadays they have a camera inbuilt. Total station nowadays they have an inbuilt camera which gives you an option to get the imagery of the target points. It can work in robotic mode, so it's one-man operation, and it also operates as a laser scanning. It's even getting better nowadays. We have a total station integrated with laser scanner, which are very precise. It can give you real-time data, and it allows you to remote and local coordinate of operation. So you have a data recorder or remote control, and you don't have to be on site in terms of safety. This chart is very interesting. It shows you different method and evolution of the larger scale dimensional metrology system during the time and their accuracy or related accuracy. So you can see the accuracy hasn't improved that much. Like we do have a very precise device, but we used to have it in the past as well. There was a huge improvement from about 1950 to 1917, but since then the accuracy is pretty much not hugely different. The accuracy of distance measurement has improved dramatically, but not angle measurement. But yeah, we have the range of options to choose, but for us to choose the best system, first we need to consider the cost, the accuracy requirement, the geometry, the complexity of the machinery, the surface of the machinery, whether it's the contact or non-contact. So all those things need to be considered to choose the right system to use. So it's basically fit for purpose. Planning of larger scale dimensional projects is pretty much like any other planning we have in surveying. We have to make sure that we have a proper techniques. First of all, we should make a decision about what data format we want, what really want to have as an output. Based upon that, we can choose which system you want to have, and obviously you have to consider many things like geometry, limitation on site limitation, environment, all those things, and then you go through the data acquisition, and then you go on instrument type and model, and then you go to the processing bit and process the data you just collected, and then from that you can go to the requirement and see whether it's fulfilled what you want to achieve or not. So considering the instrument itself, you need to consider time frame, object size, environmental condition. So all those things need to be considered. So if you're measuring the small scale object or larger scale or medium size, you might have different system for each of them. If you want a very precise method, whether you can, like, what is the maximum range you have from your location to the target, can you go closer or not, is another limitation. So all these things need to be considered. In summary, we covered larger scale dimensional metrology, the system measurement techniques which has been used in this area. We talked about the different type and application of the larger scale dimensional metrology, which is mostly industrial metrology. Hopefully we covered all the area you need to know. It's just an introduction to metrology. Obviously, if you want to learn more, there are always reading material. I put some recommended reading material which are not accessible, so it's not going to be in the exam. It's just for your interest, and you can go and read them. There is always, in future, I think there is an increasing use of laser trackers and radar. That's why we try to cover that in this course, especially if you ended up working as a monitoring survey or deformation surveys or precision engineering surveys, which some of you may have. Then you have an insight of what are the tools and how they're going to work. This is the quote of the day. You can go and read it yourself. Thank you for listening to me, and hopefully this lecture covers all the material in Module 7. And if you have any question, you can ask me on the study desk. Thank you.